Download this code from codegive.com, link in the description below. Immutable APIs, Mutable internals, a Scala design case study. This tutorial explores a powerful and often overlooked design pattern in Scala, exposing an immutable API while leveraging mutable internals for performance and efficiency. We'll dive deep into the motivations behind this approach, its benefits, trade-offs, and best practices, culminating in a practical code example illustrating its implementation. Why immutable APIs? Immutability has become a cornerstone of modern software development, particularly in functional programming paradigms like Scala. Here's why. Thread safety. Immutable objects are inherently thread safe. Multiple threads can access and share the same immutable object without the risk of data corruption or race conditions. This significantly simplifies concurrent programming. Reasoning and predictability. Immutable objects don't change state after creation. This makes it much easier to reason about your code. You can trust that the object's value remains constant, simplifying debugging and testing. Referential transparency. Immutable objects exhibit referential transparency. You can replace an expression with its value without changing the behavior of the program. This makes code easier to optimize and refactor. Caching and memoization. Since immutable objects never change, their results can be cached and reused without fear of invalidation. This can dramatically improve performance for computationally expensive operations. Simplified data structures. Many functional data structures, like immutable lists and maps, rely on immutability for their correctness and performance. The performance bottleneck of pure immutability. While immutability is desirable, a purely immutable implementation can sometimes introduce performance overhead, especially for operations involving frequent modifications to large data structures. Each modification typically requires creating a new copy, which can be expensive in terms of both memory allocation and CPU time. Consider a scenario where you need to build a large list element by element. Using a purely immutable list in Scala would involve repeatedly creating new list instances for each added element. This operation has a time complexity of (n)(2), because each prepend, : creates a new copy of the existing list. Immutable API, mutable internals, the sweet spot. The immutable API, mutable internals pattern addresses this performance challenge by providing an immutable interface to the user while utilizing mutable data structures internally for efficient computation. This allows you to reap the benefits of immutability for your API consumers without sacrificing performance for internal operations. How it works. 1. Expose an immutable API. The public methods of your class should return immutable objects or new instances representing the result of an operation. The user should not be able to directly modify the underlying data. 2. Use mutable internals. Within the class, use mutable data structures and algorithms to perform operations efficiently. This is where you can take advantage of in-place updates and optimized mutable collections. 3. Controlled mutation. Ensure that the mutable state is carefully managed and encapsulated within the class. Avoid leaking mutable references to the outside world. The goal is to confine the mutation to the internal implementation details. 4. Defensive copying. If necessary, when returning data from the internal mutable state, consider creating a defensive copy to prevent external modifications. This ensures that the returned object remains immutable. Benefits of this approach. Best of both worlds. Offers the benefits of immutability, thread safety, reasoning, while allowing for performance optimizations using mutable structures. Encapsulation. Hides the internal implementation details from the user, promoting a cleaner and more robust API. Flexibility allows you to choose the most efficient data structures and algorithms for internal operations without compromising the immutability of the API. Performance improvement can significantly improve performance in scenarios involving frequent modifications or complex computations on large data structures. Trade-offs and considerations. Increased complexity. This pattern can add complexity to the code, as you need to carefully manage the mutable state and ensure that it is properly encapsulated. Potential for bugs. Improperly managed mutable state can lead to subtle bugs, especially in concurrent environments. Careful testing and code review are essential. Synchronization. If necessary, if the class is accessed concurrently, you might need to use synchronization mechanisms, like locks, to protect the mutable state. However, careful design can often minimize the need for explicit synchronization. Defensive copying costs. Defensive copying can add overhead, so you need to consider the cost-benefit ratio. In some cases, it might be acceptable to expose a read-only view of the internal mutable state. A practical example, immutable circular buffer. Let's illustrate this with a Scala example, an immutable circular buffer, also known as a ring buffer. A circular buffer is a fixed-size data structure that behaves as if the beginning and end are connected. When the buffer is full, new elements overwrite the oldest elements. Explanation Immutable API The circular buffer class is designed to expose an immutable API. The enqueue and dequeue methods do not modify the existing circular buffer instance. Instead, they return new instances with the updated state. ToSec also returns a new sec. Mutable internals inside the circular buffer class, the buffer, an array head, tail, and size fields are mutable. These mutable fields allow for efficient in-place updates. We use the modulo operator, %, to handle the circular nature of the buffer. Controlled mutation. The mutation is strictly confined to the internal implementation of the circular buffer class. The mutable fields are private, and the outside world cannot directly access or modify them. Defensive copying. In enqueue and dequeue, we clone the internal buffer array before modifying it. This ensures that the original circular buffer instance remains immutable, and that the new instance doesn't share mutable state with the old one. We also null out the old value for potential garbage collection hints. Immutability on apply and ToSec. Apply throws an exception when index is invalid, ensuring that the program does not proceed with bad data. ToSec creates a new, immutable sec object, returning a defensive copy of the circular buffer's contents. This prevents the caller from modifying the internal state of the buffer. Usage example Key takeaways The immutable API, mutable internals pattern is a powerful technique for balancing immutability and performance in Scala. It's especially useful when you need to perform frequent modifications to large data structures internally. Careful encapsulation and management of the mutable state are crucial for correctness and thread safety. Always consider the trade-offs between performance and complexity. Defensive copying plays a vital role in maintaining the immutability of the API. Scala's features like private constructors, clone method and expressive type system are well suited for implementing this pattern. This example provides a solid foundation for understanding and applying the immutable API, mutable internals pattern in your own Scala projects. Remember to carefully analyze your specific use case and weigh the benefits and trade-offs before adopting this approach. By thoughtfully combining immutability with mutable internals, you can create robust, performant, and maintainable Scala applications.